in logic is to talk about the logic of quantum paradoxes, which to me contains things which are fascinating, both in what it throws back for logic and structural analysis of semantics itself, as well as being very important in our attempt to understand quantum advantage in quantum computing and more generally information processing tasks. But let me begin with a sort of meta contradiction. Um, so quantum mechanics is a physical theory confirmed by observations. Can we observe a contradiction? Surely not. I have no idea what it would mean to observe a contradiction. And on the other hand, why do we believe quantum mechanics? I mean, we're almost forced to believe it because it's the only way we have of understanding, the only way we found of understanding a multitude of phenomena. It's sort of confirmed every day with things that people do in the laboratory. So it best explains what we observe. So how do we come from these two things, an empirically grounded theory and the fact that we can't observe contradictions, to speak of quantum paradoxes? In a sense, I mean, to speak of quantum paradoxes, it's not actually my preferred terminology. I think it's the one that is nice to use to sort of catch the attention. But what we really mean is that while our observations are individually consistent, what else could they be? But jointly, taken together, they contradict our reasonable assumptions, which reflect a classical conception of reality. And this is what I'd like to explain in this talk. So, according to quantum mechanics, as we say, our best confirmed physical theory, we cannot measure or observe all properties simultaneously. This is an essential point here. So what we can observe at a given time, performing operationally a given measurement, is certain subsets of properties, which in the usual formalization are represented as commuting families of observables. And these subsets give us overlapping observational windows onto the quantum system. So in effect, what we can observe are partial views of the system, assignments to a subset of the variables. Now, we might think that this is just because of limitations of our apparatus, limitations of our current theoretical framework, but in fact, on pain of observing a contradiction, which I think we've just agreed we couldn't really meaningfully do, this is essentially so because what we learn from these quantum paradoxes or quasi-paradoxes that we're going to look at is that there is no assignment of values to all the variables, which is consistent with all these observational windows. So the observational windows are as they are. That is a matter of observation. And there is just no way of making a global assignment of values which would explain all the things that we observe. So to use my favorite mantra for this subject, contextuality arises where we have a family of overlapping pieces of data which are locally consistent, or the family is locally consistent, but it's globally inconsistent. And just before we continue, let's think that this description is sufficiently neutrally expressed that we could imagine it applying in situations other than quantum mechanics. And indeed, it does apply in such apparently down-to-earth computer science settings as database theory, for example, as well as many other things. It's increasingly becoming a topic of discussion in machine learning, for example. Anyway, to take up this mantra of local consistency and global inconsistency, let's think first of, to have a little visual metaphor, which is quite telling. Let's think that we're observing some building out in the distance, and our camera, having limited aperture, we can take snapshots of different parts of the building. So each of those parts looks perfectly reasonable in itself, as you see, And moreover, they're locally consistent in that the boundaries fit in a sensible fashion together. So this is a locally consistent family of images. Now, naturally, we would think that these snapshots must arise from some single image of the whole building that we see out there in the horizon, or that we believe is out there in the horizon. So if we try and put all these together, what we find is something you may recognize as the famous Escher painting, Escher, famous Dutch artist, called Ascending and Descending, whereas you follow the figures, you see that you seem to have a staircase that's either always going up or always going down, an impossibility in our usual physical three-dimensional space. It's worth mentioning, by the way, that this drawing of this figure was suggested to Escher by Roger Penrose and his father, I believe, in a correspondence that they had. And Penrose himself has written on the mathematics of visual paradoxes. Okay, so this is a sort of metaphor for local consistency and global inconsistency, but in the end, after all, this is a visual paradox. We may dismiss it as a mere oddity, but we find in quantum mechanics that really it's right there unavoidably in our most successful physical theory that increasingly lies at the root of all our current cutting-edge technologies. And the paradoxical features we're going to discuss fully entered the mainstream and the physics establishment a couple of years ago in the award of the Nobel Prize in Physics to Alain Aspect, John Clauser, and Anton Zeilinger for their work on Bell tests, experiments that establish the violation of Bell inequalities. The key experiments that were generally regarded as loophole-free were a bit more recent, about 2015. There was a long history there, but these were the pioneers who blazed the trail for that. So this is as real as any other part of physics, we can say. Now, the usual sort of schematic picture you will see in discussing what a Bell test looks like is that we prepare some state, some entangled state, and dispatch an entangled pair of photons or whatever it might be, and send one of them to a measuring station somewhere associated with Alice, one to Bob, and then it's important in this non-locality test that these are sufficiently far apart that there's no they're space-like separated, so there's no time for light to travel between them in such a way that each can know what the other one has had as their what the other one is doing. And then each of them independently has to choose a measurement setting and perform a measurement at their device, and we then collect the outcomes. So this is still the schematic for the classic kind of Bell test, which was exactly what led to this work that received this Nobel Prize, and it's also what's used in things like quantum key distribution and similar applications. Now, there's another way of looking at this, an isomorphic way of looking at this, which is quite pleasing for computer scientists or logicians, where we look at it as a game. Then we have a clear-cut information processing kind of task where we can express what's going on in the Bell experiments in this game form. So the idea here is that we have two players, Alice and Bob, who are trying to achieve a coordinated response to inputs from a verifier. And the key point is that Alice and Bob each is put in a separate room. Their mobile phones are taken away. The rooms are enclosed in Faraday cages. Of course, in the ultimate, they're space-like separated, but anyway, they can't communicate with each other while playing the game. And the verifier makes one input to Alice and one input to Bob, and they each have to, separately, without knowing the input that the other has received, produce an output. So the most famous version of this is the so-called XOR game. So we have binary inputs for Alice and Bob and binary outputs. They're not allowed to communicate during the game. And we have this winning condition that the exclusive OR of the outputs has to be equal to the conjunction of the inputs. Now, to parse this condition, these are Booleans, of course. If you think about it, on the three lines of the truth table where the conjunction of x and y is false, we're saying that the exclusive OR is false, which means that A and B have to have the same value. They have to be correlated. Whereas on the final line, where x and y is true, then the exclusive OR has to be true, meaning that A and B have to be anti-correlated. So we can write down these cases here, and if we think of a probabilistic strategy for how Alice and Bob determine their outputs, we see that in the three cases where the inputs would make the conjunction false, the outputs have to be correlated, they have to be the same, and in the final case, they have to be different, they have to be anti-correlated. So this is a little expression for the success probability of some given strategy, which gives you a probability for producing the outputs A, B, given the inputs X, Y. And we can write all this down as a little table like this. And here I'm showing you a particular such strategy. You see that on each row, we have a combination of inputs from the verifier and then a distribution on the outputs received in response by Alice and Bob. So this is their probabilistic way of choosing outputs given their inputs. Now, if I show you this table, you see, so I mean, just to be completely clear about this, the highlighted entry here is saying that this is a strategy such that when Alice gets input 0 and Bob gets input 1, then 1/8 of the time, Alice outputs a 0 and Bob outputs a 1. And you see that on each row, the numbers sum up to 1 and give us a probability distribution. And if we think about what the winning condition is, this is to get the same outputs on the first three rows and the anti-correlated different outputs on the final row. So if we sum up those numbers, we get this winning probability, assuming that the verifier has uniform probability of choosing the inputs. Now, as it stands, I've just shown you a table of 16 numbers, and it's not clear whether this is something to be interested in or not. But actually, this is, in the circumstances we're thinking of it, this is something to be very interested in. This is exactly the kind of thing, verification of which led to that Nobel Prize we were just mentioning. Because using classical resources, where Alice and Bob can't communicate, so maybe they could initially agree something before they started playing the game, but while they're playing the game, they can't communicate. The best they could possibly do is to get a probability of success of 3/4. And here we see a strategy that gives us something larger than that. Now, how could we get a probability of 3/4? Well, the stupidest thing we could imagine is that Alice and Bob simply agree that since 3/4 of the time, for 3/4 of the inputs they're going to get, giving the same answer will win, they could simply, for example, both agree to give 0 as their output, whatever their input is. Or they could equally well agree to both give 1 as an output, whatever their input is. And you see that indeed 3/4 of the time, that strategy will lead to them winning. Completely stupid as it is. But not only is that a very simple strategy, it's actually the best you could possibly achieve using the resources of classical information processing, including shared randomness, where they sort of have some whatever flipping of coins or whatever they might do in advance before they start playing the game. So how do we know that's the best they could possibly do? Well, the proof of this uses and is essentially the same as the use of Bell inequalities. So this is exactly the principle underlying Bell's theorem and everything that's followed from it, leading to those Nobel Prizes and leading to a great deal of the work that's gone on in quantum information and quantum computation. So what we see is that table, as it stands, I mean, we're going to come back to this, by the way, I mean, this idea of Bell inequalities in just a moment. But let's just accept that for a moment. So we see that the Bell table exceeds this bound. So is it science fiction? Well, no. The Nobel Prize stands as a testament that it's not science fiction. This table is quantum realizable using an entangled pair of qubits. So it shows that already that quantum resources yield a quantum advantage in an information processing task. Of course, the current efforts are to do this much more widely and for more interesting tasks, but the principle is already here in this basic form of Bell's theorem. So is it science fiction? Well, no. Experiment, observation, tells us that we can indeed achieve these more than classical correlations performing these Bell experiments. But let's come back now to the question of Bell inequalities. So I hope that all of you have heard, at least in passing, about Bell's theorem and the accompanying notion of Bell inequality. And you may well have seen a proof of Bell's theorem in some form. But what I strongly suspect that you have not heard is a general definition or explanation of what a Bell inequality is. So this is as a sort of somebody coming from logic, theoretical computer science, and so forth, into the world of quantum foundations and quantum information. One of my favorite kinds of questions I like to ask is that the area is full of wonderful examples, but I like to ask, what are they examples of? And try and answer that question. I hope as logicians we can all appreciate that this is a good thing to do. Sometimes our physics colleagues are harder to persuade. In any event, what is a Bell inequality? Is there a general notion, in fact, general enough to be applicable not just to this particular form of Bell experiment, but to some much wider notion of contextuality? And even better, is there some general principle from which all Bell inequalities can be derived? And in fact, an answer to this question was given in a paper that I wrote with Lucian Hardy, a well-known researcher in quantum foundations, from some years back. We called it, perhaps unwisely, logical Bell inequalities, because it is about a certain connection between Bell inequalities and logic, a surprising connection perhaps, but it is exactly these inequalities on probabilities which are famously associated with Bell's theorem. And in fact, this answer to the question, what is a Bell inequality, also provides an answer to a much older question of George Boole, going back to 1851, on what he called the conditions of possible experience, which we'll come to in a moment. But firstly, I'd like to actually derive a basic form of this idea of logical Bell inequality. It could be done in one slide in a very simple way. So I think one proof is worth a thousand motivations if it can be given very succinctly. So we have some propositional formulas describing events of some kind, and we're able to associate probabilities with each of these formulas. So we have some distribution over the events, and then we get probabilities from them. So if I told you nothing else, then all we could say is that these numbers, pi, are numbers, real numbers in the unit interval between 0 and 1. But now let's take one further assumption, a purely logical assumption. Suppose that these formulas are not simultaneously satisfiable. So no assignment of values to the variables makes them all true, which tells us, and here, by the way, we're operating just in ordinary classical propositional calculus, the conjunction of any n minus one of them must imply the negation of the nth. That's just another way of saying they're not simultaneously satisfiable. And we can take the contrapositive form. If the nth is true, then one of the others must be false. Okay, so that was very simple propositional calculus. And then we have one other line, which is just a little elementary probability theory. The first step is just the observation that probability is monotone. Any probability measure is monotone. The probability of a larger set is greater than or equal to the probability of a smaller set. The second inequality is known in computer science as the union bound. The probability of a union is less than or equal to the sum of the probabilities. It's also known, incidentally, as Boole's inequality, and it can be seen as the first and simplest of a sequence of what are known as Bonferroni inequalities. But it's a very simple one. It's much more straightforward than anything to do with inclusion, exclusion, and so on. And then we simply use the formula for the probability of a complement, and we do a little tidying up, and we obtain this inequality, that on the assumption that the formulas are not simultaneously satisfiable, they're bounded by n minus 1 if there were n of these formulas. So I hope this little derivation is clear. If anyone has an objection, now is the time to raise it, because we will derive a striking conclusion from it. Okay, so here is our table again. As we've said, this table for a strategy as we can think of in the Alice-Bob game can be obtained in quantum mechanics by using a maximally entangled state and suitable choice of measurements for Alice and Bob. It can be compared experimentally with Bell tests, and it gives a basic example of quantum advantage. Now let's come back to our table and analyze it from the point of view of this logical Bell inequality. So what I've done here is the same table. I've highlighted the winning entries. So remember, on the first 3 rows, Alice and Bob win if they have correlated outcomes, and on the final row, they win if they have anti-correlated outcomes. So these are the highlighted entries. And if you sum them all up, you get 3 1/4. Well, now let's analyze these events from this logical perspective, so that the formula that we can write down that corresponds to the winning events on each row, we see just writing that if we think of logical variables corresponding to the outcomes of the various measurements, then on the first 3 rows, it's just saying it's the if and only if of the 2 variables concerned. And on the final row, it's the exclusive or, so correlated and anti-correlated. But now it's very easy to see that these formulas are not simultaneously satisfiable. Let's do a little proof of this, because we may recognize in this another famous logical pattern. So let's start from A2 down here. Well, using the third formula, we can replace this by B1. Using the first formula, we can replace this by A1. And using the second formula, we can replace this by B2. And what we have on the final row then is B2 exclusive or B2, which certainly can never be true. The other logical pattern you may recognize here is actually a kind of a Liar cycle, an extended form of Liar paradox. In any case, these formulas are not simultaneously satisfiable, so simply applying our little result here, we know that the sum of the probabilities must be bounded by 3, since there are 4 formulas. But actually, we violated this inequality by 1/4, as we can see. Now, you may think, have I pulled some sleight of hand on you? Because we seem to derive this inequality. Well, we did derive it in a perfectly clear way. There is a subtle point, a subtle assumption, which is contained in this derivation. Perhaps I won't, I mean, you can probably decide for yourself what it is, but perhaps we'll leave it over to the end. There is an important assumption which is completely related to the local versus global issue that I was mentioning as the essence of these quantum paradoxes. At any rate, what we see in the table is a violation of this inequality. And this is exactly the kind of violation that is shown by the Bell experiments and the work we were mentioning. Now, we can put this a bit more generally. This was a particular case, but to generalize a little, given a family of propositions, we can say it is K consistent if the size of the largest consistent subfamily is K. And then in a similar kind of way, we can argue that whenever we get some probability assignment on all the events described by these formulas, then the sum of these probabilities is bounded by K. So the particular case we derived was where K was n minus 1, but it generalizes in this fashion. And now the main sort of result in this paper with Lucien on logical Bell inequalities is that all Bell inequalities arise this way. This is a completely general description of Bell inequalities. So formally, the result is a rational inequality is satisfied by all non-contextual empirical models if and only if it is equivalent to a logical Bell inequality of the above form. So I haven't explained all the terms, but I mean, it's indicating that this is a very general thing. So the beautiful thing that we see here is this interplay between logic and probability. In fact, here we can invoke two pioneers, one of logic and probability, George Boole, and the other, John Bell. So George Boole, of course, was a pioneer of both logic and probability, and we can say of computer science. And there's a remarkable connection between his work in probability and the idea of Bell inequalities. And this was first pointed out by the philosopher of science Itamar Pitovsky in his beautiful paper on George Boole's conditions of possible experience and the quantum puzzle. So Boole referred rather sonorously to the asking for the conditions of possible experience, possibly in a slightly facetious kind of Kantian way. Anyway, the connection with all this is discussed in a paper I contributed to a volume in honor of Itamar, who sadly passed away a few years ago. Well, his summary of Boole's problem is very nice. We're given rational numbers which indicate the relative frequencies of certain events. If no logical relations obtain among the events, the only constraints imposed are that they each be non-negative and less than one. If, however, the events are logically interconnected, they refer to equalities or inequalities that obtain among the numbers. The problem is thus to determine the numerical relations among frequencies in terms of equalities and inequalities which are induced by a set of logical relations among the events. The equalities and inequalities are called conditions of possible experience. So if we write this out slightly more formally, we get this sort of setup, and we can say the key question is what numerical relations between the probabilities, specifically which linear inequalities, can we infer from the logical relationships between the events? And so really, the sort of result I was just mentioning gives a full logical answer to Boole's problem. Pitovsky didn't give an answer of this form. I mean, he did some beautiful work relating the computational complexity of the problem, but he did, in one of the things he said, suggest that he may have envisaged the possibility of some result. He says, in fact, all facet inequalities for the polytope correlation polytope, as he called it, should follow from Venn diagrams, that is, the possible relations among n events in a probability space. And with contextuality, which we've seen manifested in this kind of violation of Bell inequalities, we're concerned with not with conditions of possible experience, the classical world of probability, which underlies also classical physics, that Boole was asking about, but rather with quantum conditions, as we may say, of impossible experience. Of course, our experiences have to be possible if they happen, but in terms of this global putting of things together, we have impossibilities. So let me give at least a hint of a more general perspective on this. We've seen a table. What is that table an example of? So we have a general setup of measurement scenarios where we have, it's useful to have where we pick out those subsets of the variables which can be measured together. This, as we said earlier, is a key point. We can only have these overlapping windows of observation. We can't observe everything. And this is given by this family of sets, which since they'll always be closed under subsets, we can take this to be a simplicial complex and an abstract simplicial complex. And then we have outcomes for each of these. And we can already begin to take this table and write it in a form that we'll come back to this in a moment, a more suggestive topological form. And so that's the format, the type, if you will, the measurement scenario. And then when we put in the actual data into this structure, we get something we call an empirical model, which is a probability distribution over the joint outcomes for each context. So this is where we put in the numbers corresponding to a probability distribution on each row of the table. But now the shape of the tables themselves have been significantly generalized in this format. And this is really the generalization of going from a simple Bell test, Alice-Bob Bell test, to a much more general contextuality scenario. And an important point is that a mathematical condition correlates perfectly with a very important physical condition, which is that when we look at distributions of variables, they are independent of the distribution on the variable is on the outcomes of the variable is independent of which context the variable was measured in. And this is here is rendered as a sort of functoriality if we restrict marginalization, if you like. So there are consistent marginals. That's really what this is saying. Okay, well, now we can define, I mean, having given this bare bones, you see we have a family of data which is locally consistent, which is what this generalized no signaling is a sort of formalization of on the probabilistic level. And now we can talk about what global consistency is, and this is what gives us our definition of when something is contextual. So an empirical model is non-contextual if there is some distribution on all the variables, such that if you marginalize it to each of the context, you get exactly the observable distribution. So we have a bunch of observations. Can we derive them all from global information and global consistent description, which from a classical point of view is surely how things have to be. And we say that the model is non-contextual if this is the case. And we call, for geometric reasons that we're sort of going to hint at, we'll call such a global distribution, a global section. It's the result of gluing all the local pieces of information together. And we say that if no such global section exists, the empirical model is contextual. Contextuality arises where we have an obstruction to this gluing of the local information together. So this exactly gives formal content to our favorite slogan that contextuality arises where we have a family of data which is locally consistent but globally inconsistent. Okay. Right. And the import of Bell's theorem and similar results is that there are empirical models arising from quantum mechanics, things which can be subject to experimental verification, which are indeed contextual. So this is the way the world works. We can't always take the observable local information and glue it together in a consistent fashion. And that's, of course, remarkable on a conceptual level, but it's also, and I don't really have time to talk about this, it's also the seed from which most of the known examples of quantum advantage arises in quantum computation and quantum information. After all, if we're going to do better using quantum resources that we can do using classical resources, it must be something non-classical about quantum mechanics that we're taking advantage of. And this principle is exactly the essence of quantum non-classicality. Okay, so let's come to these bundle pictures. I already showed you a quick glimpse of one, but I think this is a beautiful way of looking at these things. We have tables we're already familiar with. Here is not actually the same table as the one we saw. It's a variant, and I haven't even put the probabilities in. I've just put possibilities. In other words, tick means can happen, has probability greater than 0, and cross means has probability 0, can never happen. And this particular construction is actually due to Lucian Hardy, as known as the Hardy paradox, in fact, standardly, and Lucian was the co-author on the logical Bell inequalities work. So how are we going to draw this in a very different way that is very suggestive and suggestive in a sound fashion? We're going to sort of take the variables we're measuring and make these to, as it were, a base. So this will be the base of a little discrete bundle we're going to draw. And we're going to put an edge between two of these measurements in the base if they can be performed together. And the nature of Alice-Bob experiments is that Alice, in any given round of the game or instance of performing the experiment, Alice can only perform one of her measurements, say A or A prime. and similarly Bob can only perform B or B prime, but because they're separated from each other, they each can work independently of the other, and they each can freely choose a measurement. So any Alice measurement is adjacent to any Bob measurement, but notice that we don't have adjacencies between A and A prime and B prime. So this is the bundle. Now we have fibers for this bundle, which give the possible values that we can receive as values of these variables or outcomes of these measurements. And we're going to put edges between outcomes if they are possible joint outcomes. In other words, if they don't get probability 0 in this table. So you see on the first row, all the combinations are possible, and we put in all the edges. But on the second row, one possibility is impossible, so we only have 3 edges, similarly on the third row, and similarly on the fourth row. So that gives us a little bundle. And now, what is a consistent explanation of some particular thing we may see? So suppose that, so firstly, so a consistent explanation would be there's a way of assigning values to all the variables, which is consistent with a particular thing we happen to see. So we can see that, for example, if we happen to see that A gets 1 and B gets 1, we can fit this into an assignment to all the variables, which lives in this bundle. So it's consistent with all the observations we could make under all measurement settings. So this is the highlighted red square. So in other words, we have a closed path. You may think of it as a kind of discrete holonomy if you like to use fancy terminology here, which gives an account for those particular values that we can see. But the reason that the Hardy paradox is a Hardy paradox is that if we make a different choice, for example, we look at this value where A gets 0 and B gets 0, we can now try and do the same thing. We can find one of these closed univocal paths, which gives a consistent value for each variable. Well, we only have one choice here. And then we only have one choice there, and then we only have one choice there, and you see we haven't come back where we started. So visually, we see immediately that we can't do this. And the same is true, of course, if we go around the other way, it's completely symmetric. So we can't get back, given that particular choice of starting point, to where we came from. So this suggests a topological nature to the phenomenon of contextuality. In fact, in the sort of whole story, it turns out there's a hierarchy of contextuality. What we saw in the Hardy paradox is what we call logical contextuality. The Bell inequality is witnessing probabilistic contextuality, where you really need to see the probabilities to see that there's no way of gluing the information together. And there's even something stronger than logical contextuality, what we call unimaginatively strong contextuality, and this is witnessed by another actually famous example in quantum information, the so-called Popescu-Rorlich box. We'll come back to this in a moment, but you see that this, where we have, well, in fact, let's see it right here, because if we take our Bell table that we were looking at earlier, we forget about the probabilities and we just again write the winning conditions, the support of the winning conditions as a bundle. Then what it gives us, I mean, here we have sort of, as it were, overspill of probabilities. But if we only focused on the winning conditions, and this is actually corresponds to a very famous thing called the CH-SH inequality, the Clauser-Horn-Shimony-Holt inequality. But anyway, if we focus on these winning conditions, and we draw the corresponding bundle, we see that it's a kind of discrete version of the Moebius strip. And wherever you start, when you come round, you don't get back where you started. In fact, you have to go around twice to get back where you started. This is actually exactly an example of a liar cycle, where you have a sequence of statements that eventually, after the nth one of the sequence, will contradict the first one. So it's a liar four cycle, in fact. So in this way, we can at least suggest here a link, I think a beautiful link and a fruitful one there's still much more to be understood on, between fundamental physics, probability, logic, and topology. So this is the image, I hope you will remember. But of course, you might say, well, I've shown a little example, but is there something more general going on here? And in fact, there is. Um, in elaborating the mathematical formalization here, the idea is that the possible events occurring in a given context vary functorially in the sets of measurements, the fibers over the base in the bundle diagram. The functoriality is very important here, and it actually corresponds to this sort of no signaling or no disturbance principle, which is physically important. The actual data is given by distributions over these events, again described functorially. And some of you familiar with coalgebras and so on will know about the distributions functor, or monad, which plays an important role here, and which can be parameterized so that you can have different semi-rings. So you can either have probabilities or possibilities, as in the examples we were just looking at. And all of this fits perfectly into the language of sheaf theory, which is as it should be, because sheaf theory is exactly the mathematics of the passage from local to global and obstructions to this passage. And contextuality is exactly about such obstructions. And and justifying the sort of suggestion of topology, these obstructions can be formulated in terms of cohomology, which measures the logical twisting of the fibers. So actually, we can take the check cohomology and use this as a criterion of the pre-sheaf that we have here from this functor, and use that as to give a characterization of contextuality. The logical twisting relates to paradoxes such as the liar paradox. And as we've seen briefly, Bell inequalities can be characterized in terms of logical consistency conditions on events, Boole's conditions of possible experience. And, there's a lot more aspects to the story. There's a resource theory of contextuality and the notion of simulation between contextual systems. And on the quantitative side, there are key measures of contextuality, such as the contextual fraction, which have proven to be very fruitful and useful. And there are many connections with logic and computation. I mentioned links with database theory. I have a paper on relational databases and Bell's theorem, and this has stimulated some database theorists to do some work in the area of these connections. In particular, let me mention beautiful recent work by Albert Atserius and Fokion Kalaitis, also with constraint satisfaction. And there's a beautiful result due to Vorobyev from the 1960s, which also plays a role here. Okay, well, I could finish here, but if I have another 6 or 7 minutes, I could just say something else. So if
you have plenty of time.
Okay, so I thought it might. I mean, I've shown you these things, and this is the way I like to look at. I've found most fruitful to look at these things, but I thought it might be useful also to say a word about connections with something that people may have heard of, be somewhat familiar with, traditional quantum logic. So let me finish with that. So of course, the sort of the person who gave the sort of crystal clear mathematical formulation of quantum mechanics, which is still being used to this day. This is ordinary quantum mechanics, which is the thing that gets used in most work on quantum information and quantum computation, was John von Neumann. And there he identified quantum properties or propositions as projectors on a Hilbert space, which so they're bounded, self-adjoint, and idempotent operators. And as is well known, projectors correspond bijectively to the closed subspaces of Hilbert space. But sometimes correspondences can carry some dangers. Subsequently, and also very famously, Birkhoff and von Neumann, so Garrett Birkhoff, one of the main founders of modern universal algebra and lattice theory, so they wrote a famous paper, The Logic of Quantum Mechanics, which proposed the lattice of closed subspaces as a non-classical logic to serve as the logical foundations of quantum mechanics. I mean, on the whole, well, okay, I mean, and the idea is that logical operations, you have a lattice. I mean, it's immediate that closed subspaces are closed under intersection, so this is a complete lattice. And so you could interpret and or as logical operations just directly from this lattice. And famously and notoriously, distributivity fails, which you get orthomodularity instead, but it's um, a fairly pale substitute. But there's a kind of objection. I mean, on the whole, let me say, in my opinion, quantum logic has not been in this form, has not been a great success. And one of the main ways of seeing this is precisely that it hasn't turned out to be very useful in the whole modern development of quantum information and quantum computation. So it doesn't give a very good account, or much of an account, of the whole sort of Alice Bob world. There are issues with tensor products, and it hasn't been that useful. Now, a sort of original sin in this setting, and why I was saying it can be dangerous when you have a bijective correspondence between things, is that it's very easy to say that, well, we can take intersection of closed subspaces, so we get conjunction can be defined generally. But operationally, where measurements, basic dichotomic measurements, are represented by projectors, only commuting measurements could be performed together. This was the very point that we started with. So if we take, the two projectors operationally, we can ask what is the operational meaning of the conjunction when those projectors do not commute. Now, of course, it's perfectly true that if you take the corresponding subspaces and then work out there will be a projector that corresponds to them, but it's not going, in general, if they don't commute, going to be related to the projectors you started with in any particularly meaningful way. And this consideration led Kochen and Specker to a somewhat different approach. And this is in their famous paper, The Problem of Hidden Variables in Quantum Mechanics, which is really the foundation of the theory of contextuality. By the way, it's worth remembering that Kochen and Specker were logicians. What they used, rather than the lattices of closed subspaces, are partial Boolean algebras, where instead of allowing arbitrary conjunctions and disjunctions, they treated them as partial operations, which could only be formed with respect to commuting projectors. So that means, in fact, that there's a trade-off. Instead of having this non-distributivity, you have partiality. So it's another way of so distributivity is a way of getting at incompatibility. Non-distributivity, I should say, is a way of getting at incompatibility, and partiality is another way, and I think conceptually a better one. There's a beautiful paper by Simon Kochen, which shows how a large part of the foundations of quantum theory could be developed in this framework. Well, what is a partial Boolean algebra? So the key thing is we don't just have a partial structure, we have, as it were, a positive thing, a binary relation of commensurability or compatibility on the underlying set. And then the negation is total, and we only have the conjunction and disjunction being defined on compatible arguments. So their domain is the compatible pairs. And you need a condition which can be put in elementary terms. I mean, you only need to talk about three things at a time. It's basically saying that every set of pairwise commensurable elements is contained in some larger set, which is a total Boolean subalgebra. So we can think of a partial Boolean algebra as having this family of ordinary total Boolean algebras contained within it. But there are warnings here, and I'll mention a reference that will point out some of these warnings. The key warning is if you think, well, okay, you have this family of total Boolean subalgebras, I mean, then surely all the information is there. Well, in general, if you took the co-limit of those, you would get an inconsistent theory where true equals false. And this is so lurking in this structure is the latent classical inconsistency or paradox. Anyway, the key example of a partial Boolean algebra are indeed the projectors on a Hilbert space, and conjunction becomes partial, defined only on commuting projectors. Negation is just, algebraically, the negation of a projector P is 1 minus P, or you can say it's the orthocomplement. That's a total operation, and disjunction is actually is definable from conjunction in the usual way. And morphisms of partial Boolean algebras are maps preserving commensurability and the operations wherever defined. So this is the world of partial Boolean algebras. Now, the famous theorem of Cochin and Specker says that as soon as you have a Hilbert space of dimension at least 3, and you take this partial Boolean algebra of projectors, there is no partial Boolean algebra homomorphism into the 2-element Boolean algebra, the one we really like. So there's no way of having assigning classical truth values consistently to the projectors, in the sense that in any total Boolean subalgebra, it would form a homomorphism. This is a very powerful result. It's saying there's no assignment of truth values to all propositions that respects logical operations on jointly testable propositions. It immediately implies, using known things, that there's no homomorphism into any total Boolean algebra. It also tells you that the spectrum of a partial Boolean algebra is empty, because a point of a Boolean algebra in classical stone duality is a homomorphism into 2. And for these interesting partial Boolean algebras, there are no points. So we might think that this kills off the idea of a kind of duality theory for partial Boolean algebras. However, in work with Rui Suarez Barbosa, we have developed a duality which generalizes stone duality on finite things, but in general, it generalizes the Tarski-Lindenbaum duality for complete atomic Boolean algebras. So even though we don't have points, we do have atoms. P of H, the projectors on a Hilbert space, is an atomic lattice, and we can develop a duality based on atoms, where instead of the standard duality with sets that you get for a completely atomic Boolean algebra, you get a duality with graphs. And these are exactly the graphs that are often drawn to give Cochin-Specker proofs. Okay, well, conditions of impossible experience. So here is a result that Cochin and Specker pointed out. They were logicians. That if you have one of these sort of interesting partial Boolean algebras to which the Cochin-Specker theorem applies, then equivalently, that's saying there is some propositional contradiction. Again, we're talking about classical propositional logic, and an assignment of the elements of the partial Boolean algebra to the variables in the propositional formula, such that the formula is verified in the partial Boolean algebra. When I say verified, I mean we do the usual thing with truth conditions, but we only ever have to apply logical operations where they're defined. So we only apply a conjunction or a disjunction to compatible arguments. So what we're saying is that we can find a contradiction which is actually verified. Actually, entirely equivalently, since these things, where things are defined, behave perfectly classically, we could say that we could find some propositional tautology which is falsified. But actually, I think that's less shocking. After all, we all know about intuitionistic logic, which happily in Kripke models falsifies tautologies, A or not A, or not A implies A, and so on. We're quite used to that, but we're not so used to verifying contradictions. And of course, this is saying that the event algebra cannot be interpreted globally in a consistent fashion. And to repeat the general point once again, our local observations, real observations of real measurements, cannot be pieced together globally by reference to a single underlying objective reality. the values that they reveal are inherently contextual. And of course, philosophers are still discussing the philosophical consequences of this, and people working in quantum information and computation are exploiting the computational advantages and consequences of this. I'd like to make a point for logicians, because I want to make the point that quantum logic, or the logic of quantum paradoxes, is more non-classical than intuitionistic logic. So what do I mean by this? So let's say that a classical contradiction is a propositional formula such that classical propositional logic proves its negation. And then there's a simple observation, or simple by virtue of Glivenko's theorem, that if classical logic, if something is a contradiction in classical logic, then it's also a contradiction in intuitionistic logic. So in other words, this reflects the asymmetry of intuitionistic logic. So there are fewer tautologies, but there aren't fewer contradictions. Every classical contradiction is an intuitionistic contradiction. So this is, if you like, the safety of intuitionistic logic against admitting classical contradictions. So, we get from this immediately a classical contradiction cannot be satisfied in any sound semantics for intuitionistic logic. So no Kripke model will verify a classical contradiction. So in this sense, because we've just seen, Hilbert space and the space where we can actually measure and observe things does verify such contradictions. Now, a further note here, and let me sort of finish up on a kind of intriguing question here. We can ask, well, is it true that which contradictions can be verified in Hilbert space in this way? We can certainly prove that some contradictions, for example, that liar-for cycle I showed you earlier, cannot be verified in this way. On the other hand, obviously we can give concrete examples of those which can. So I've been interested for a while in trying to characterize in some structural way which contradictions can be realized in this way. Now, the computational lens, Nihal Shah and Anuj Dawar have shown that if you don't specify the dimension of the Hilbert space, then this question is undecidable. And on the other hand, if you bound the dimension of the Hilbert space, then I believe Nihal has now shown that it's complete for a class ER of essentially the existential fragment of the theory of real closed fields, which is a class that sits inside P space. But it would still be nice to get some kind of structural understanding of which contradictions can be verified in projectors on a Hilbert space. Okay, well, so let me leave that as a sort of question for your consideration and finish up. So I thought I'd just sort of mention and show you some of the many people I've had the pleasure of working on these things. Actually, this slide was getting kind of full. I'm very happy to also, I should mention Yoko, who I've recently worked with on connections between this kind of quantum paradoxes and dependence logic, and also then his student, Yoni Puljujärvi, who's now doing a postdoc with me. And the first person there, Adam Brandenberger, so the sort of general perspective and this chief theoretic formalism that I've mentioned for looking at contextuality was originally developed in work with Adam. And yeah, and let me just say that if you want to pursue any of the aspects of what I've been talking about further, there are lots of papers. I think they're all available on the archive, so they're easy to get at. If you can't find anything, then by all means, very welcome to contact me, but they should all be there. So it's a very rich, so in conclusion, the logic of quantum paradoxes, they're sort of, maybe it's better to say we're on the boundaries of paradox, and those boundaries are a very interesting place to be, which are very fruitful in current developments in quantum information and computation, and also, of course, challenging and suggestive from the point of view of quantum foundations. Okay, well, thanks very much. I'll finish there. Thank you.
Thank you very much.
Shall I stop sharing?
Yes, you can do that. I'm going to hand over to Zoe for the questions and answers. Maybe you can keep your slides on just in case someone wants to refer to them.
Yeah, okay. Right. So if
I'll stop the recording in the meantime, right now. Yeah.
So